I only see about half the people logged in so far, so I'll dawdle for a couple of minutes.
Miss Molnar, do you ever pay attention to the Hadron Collider that's going on over there in France?
I saw something on Twitter that implied that they had it up and running again, and I saw something that I'm assuming was a joke because they were talking about punching a hole in the fabric of the universe so that we could all escape.
I don't know about that, but I did see that they had it running at full speed, and I don't know what they were testing, but basically creating mini black holes that exist for half a fraction of a second, but mathematically would prove somehow the existence of a parallel universe. So, you know, I keep a pretty open mind. I don't know how much truth there is to that or not, but sounded
Well,
interesting nonetheless.
that would actually, I suppose, go a ways toward providing some level of proof for the 11 dimensions of reality and the multiverse theories that all
Yes, that's what it was.
coexist in terms of theoretical physics, of which I've read a fair amount. I have a favorite author whose name is Michio Keiko, who is a Harvard University professor, and I've read a number of his books as well as a handful of other ones. Brian Greene is another one who's got some really decent theoretical physics books that are light on the math end. And I've read a number of the Stephen Hawking's ones too. I've actually read some of his journal articles as well as some of his more mass market stuff. Yeah, my tensor calculus is just not that good. A lot of the proofs in the journal articles are really tough going.
Yeah, I like reading about the stuff in layman's terms.
But yeah, Michio Keiko. Actually, let me go grab a book off my shelf. I'll like show you what the cover looks like. Hang on, let me do
Okay.
spotlight so it'll be bigger.
So, Ian,
Yeah.
are you paying attention to it just for fun, or is it for work, or just as a question?
This is the guy's
Oh no,
name,
pure curiosity.
Michio Keiko. He's a Harvard professor. Okay, speaks perfect English. Okay, so it's not like a language issue there. This is one of my favorite books by him. It's called Hyperspace. It's among other things in about the 11 dimensions of reality, the four normal ones plus the other ones that are all curled up in the Einstein-Bose condensate. Segments of the universe. So anyway, but this is a guy to like look up. He has probably 10 books, but they're light on the math end. So he is one of my faves. All right, that's not everybody as I was expecting, but that's a fair chunk of the class logged in now. I'm going to do another problem that involves the partial pressures because I think that there was a lot of confusion, and so I doodled up a additional example, which I'm going to try to see if I can do on the whiteboard function. All right, so we're going to start with, and I can't do subscripts, so this is going to look a little bit weird, but nitrogen, carbon dioxide, actually that should be capital O, and neon are in a flask. So that's our starting point. And they have a total pressure of 790 torr. I'm shooting for a different pressure unit this time. And we need to know something additional about this. So the respective, I hope I could spell, moles are therefore 1.7 for the nitrogen, so 1.7 moles. And then I'm going to have 0.35 moles for my CO2 and 0.55, supposed to be 0, moles for my neon. I want to find partial pressures. This one I'm not doing involving the ideal gas law. This one is strictly using the concept of the mole fractions. So the first thing I need to do is add up my moles. So I'm going to do 1.7 plus my 0.35 plus my 0.55. And that's going to give me a total of 2.6 moles. So now in order to do my partial pressures, I need to do each one of the individual gases on top of the total moles. So for my nitrogen, then I'd have 1.7 over top of 2.6, but I'm going to multiply by my total pressure. So times my 790 torr. And this will mean that for my nitrogen alone, I have 516.5 torr. Then for my CO2, different number on the top, bottom number remains the same because my total number has not changed. And also for this one, I am multiplying by my total pressure because I want to figure out what part of that total pressure is actually due to the carbon dioxide. This one comes out to be 106.3. And then the last one, my neon, has the 0.55 on the top and the 2.6 on the bottom. Same thing, multiply by my total pressure. And that will give me 167.1 torr. I did a little bit of rounding so that I only carried them out to a single decimal place. So that may not quite exactly give me 790 if I actually added them all back together. Okay, trying to figure out where I laid my calculator. So if I went back and I added the 516.5 and the 106.3 and the 167.1, I'm close. I come up with 789.9. Like I said, I did a little smidge of rounding. This is probably a more straightforward usage of the idea of Dalton's law and partial pressures, because if I look at my 3 items here, remember the idea of Dalton's law is the parts add up to the whole. So my nitrogen is the overwhelming chunk of my total pressure of 790. I have a much smaller amount, my CO2 is 106 of the 790. And my third one, my neon, was kind of somewhere in the middle there of 167 of the 790. So hopefully maybe that makes it a little bit more straightforward. I'd pick, like, I have an almighty ton of different chemistry books in my house, and sometimes I fish out different examples to use, and I'm not sure that, especially since I was doing it digitally, I'm not sure that the example that we ended with on Tuesday was very straightforward. Questions about this particular example then?
It doesn't matter what each of the, I guess, gases are then.
No, actually it doesn't. Weirdly, you'd think that it should, but in the world of gas laws, if they are not actually undergoing a reaction, it doesn't really actually make a difference. You could almost think about this as, well, if I had a big bowl, okay, since we're heading toward Halloween, since if I had a giant bowl and I put, 2 bags of Snickers in the bowl with 1 bag of Kit Kats and half a bag of Milky Ways, it doesn't actually matter what they are. You could still count up the number of pieces you've got. That's kind of how the gases work, because they're not undergoing a reaction at this point. So yeah, the fact that I have nitrogen, carbon dioxide, neon doesn't actually make a difference. Other questions?
Yes. Can you do a quick problem with converting pascals to ATM?
Okay. Well, let me scroll down. I don't know if it'll let me scroll down or not. Okay, hang on. Let me re-invoke my whiteboard. It doesn't seem to want to let me scroll down and create a different one. Oh, there. Okay, clear. Okay, clear all drawings. All right. So you said go from pascals to something.
ATMs, atmospheres?
ATMs.
Okay, so from pascals, hang on. So from pascals to atmospheres, right? Okay. So let's do convert 135,000 pascals to atmospheres. All right, so 135,000, okay, PA. Oops. What? Why is it doing something weird here? Okay, and I'm gonna do times 1 atmosphere over 101, comma 325. All right, and then I have to do this on my calculator because it won't calculate for me on the whiteboard. So 135,000, and I am dividing by 101,325. So this would give me 1.33 atmospheres. Does that help?
Yes. So that 101,325 that's a given,
Yeah.
right?
Yeah.
Okay.
This is the value that goes with pascals.
Yeah.
101,325.
Okay. And I was looking at, I was doing a homework, and I was number 3. I was like, I don't know. It's probably the notes, but I didn't see it, so I got stuck on number 3. I was doing the homework, so I just want to.
Because if you do what I call like the equivalence thing, 1 atmosphere equals 101,325 pascals.
Okay. Thank you.
Okay. Other questions about stuff we've already covered in this chapter? All right. Let me talk about kinetic molecular theory a little bit. So kinetic molecular theory is a bunch of ideas. And part of this is based upon a bunch of assumptions which are not strictly true all the time. We're pretending that everything behaves like an ideal gas when in fact it actually probably doesn't, or at least doesn't at some of the time. So the first part of this talks about the volume of the gas particles, and they usually refer to it as virtually negligible compared to the distance between them. So think about this as if this were a page of polka dots. Well, if you gathered up all the polka dots that under normal circumstances are all spread apart, and you scrunched them all tight enough that they all touched each other, they'd only take up a little space down in the bottom corner of the page. So the gas molecules, even though you think about them as taking up space, the particles themselves are actually really small because they're molecules. There's lots of empty space in between. Part 2 is pretty true. Unless you are at absolute zero, your gas molecules are considered to be in constant motion. But that also means that the pressure that they create is mostly due to the fact that they are hitting against the walls of their container. If you had a big jar of super bouncy balls, and you shook it up, well, the fact that they are all colliding not only with each other, but the fact that they are colliding with the walls of the container is the general reason that gases are capable of exerting pressure. So number 1 and number 2 are more truthful than the next one. Gas particles neither attract nor repel. This one is kind of dubious because it depends a very great deal on what the gases are. For instance, if you had one of the noble gases, neon, krypton, xenon, helium, all of those have very little attraction to each other and also very little capacity to repel each other. But when we do a lab that is upcoming here in about a month, that's called carbonate analysis, the gas that we are collecting is carbon dioxide. And carbon dioxide is actually capable of some attractions. The oxygens in the CO2 molecule tend to loosely attract to some of the carbons in the next molecule over. So you actually get a less than ideal behavior if you're looking at something like carbon dioxide. The same thing would be true of water vapor. We know that water molecules attract each other. That's part of what holds them to each other. It's also part of what holds them into the hydrate, which is the lab that we spent the past couple of weeks doing, whether you were group A or group B. We did the hydrate lab, and once you heated up those molecules, we forced the water to separate or detach from the hydrate molecule, the salt part of the molecule. But water vapor is the gas itself. So you could get some attraction between those. Repulsion's a little harder to deal with, attraction's more common. The last one is also pretty truthful. The average kinetic energy of the particles is proportional to the Kelvin temperature. So this goes back to the idea of why we don't want to use Celsius, because Celsius has negative numbers. We don't want to put ourselves in a situation where you could have negative values for energy in terms of how fast they're moving. We want all our values to be positive. Warm things move fast, cold things move slow. Truisms of the universe. Okay, those things are actually true of many things besides just gas molecules. So depending upon which molecules you're looking at and which gas you're dealing with, some of these 4 criteria are more true or less true than you might expect. So that kind of varies a little bit. All right, I am going to use my chalkboard again. And very simple things super well. My speaker is not working. What did I do to my speaker?
Not working in what way?
I don't know. Did I lose all my audio?
No, I can hear you.
Okay. I have this weird symbol down the bottom that says my speaker is not working, but I don't know what that actually means.
Well,
You blinked out for a little bit.
Okay.
Easy.
Yeah.
It just
blinked
says
out.
speaker's not working?
Oh, that's weird. Okay.
Yeah, that's really odd.
Yeah.
Do this. Keep it down a little bit, otherwise we're getting more of the ceiling.
Mm-hmm. Just angle it differently. I have to use. There we go.
It's still kind of. That doesn't get the bottom of the chalkboard.
Second. Actually, I prefer not have to change that, so let's just try and angle it down more. Angle this even more. No, what the hell? What the hell?
Just say loosen up the thumb screws. Okay, that might work.
That's better.
All right, so hopefully that's angled. Yeah, I still am getting this weird thing that says low system resources.
Why does this have an angle? This is weird.
I don't know why it's saying that.
Yeah, let me see. Figure. Like an angle.
Oh, I'm crooked.
We're crooked to start with. There we go.
All right,
That's better.
So root mean square velocity. Okay, and part of the reason for doing this on the board is because it involves square root symbols. So the first thing is, if you look at this thing that kind of looks like, it looks like a U with a tail on the front of it, and then it has an R, M, S as its like subscript. To do root mean square velocity, you need a square root symbol. And it's going to have 3RT over M, all contained within the square root symbol there. Okay, one of the things that's unfortunately true about this particular equation is the R in this equation is not the same R that was in PV equals nRT.
Nice.
So the R for this one is going to be 8.314, and it has different units. We have joules per Kelvin times moles. Okay, so all of these things are relevant. The M that's on the bottom here is molar mass, but it's molar mass in kilograms per mole, which actually makes it kind of different than ones that we have seen up to this point in this semester, because all the other ones we've been looking at have been grams per mole, which means we have a different place that we are putting our decimal. All right, so this is the equation that we're going to be using, but I'm going to erase some of this stuff. And like I said, this is in your notes, but the way it's written in the notes, where the square root symbol is, I'm not sure is like super clear. You may have to also refer back to your textbook for this. All right, we're gonna do calculate root mean square velocity for argon at 35 Celsius. So a whole bunch of different things involved here. Okay, let's put it into the equation. The 3 never changes. It's just part of the equation. And then I'm going to put in my 8.314. And the K value, the temperature part, again, has to be done in Kelvin. Everything that's in gases is Kelvin. So I'm going to do 308 Kelvin there.
Is it mu or is it U?
It's mu, okay? It's a Greek letter mu, mu, and it looks like a U, though, with a tail on the front of it.
Because it looks like it's written U in the notes.
It should be a Greek letter.
Yeah, but
it has, depending upon which font I use, it doesn't make the little tail on the front end of the U super obvious. The only font I could find that had Greek letters in it has a really short tail on the front of it.
It's all right. I'll just make sure that it's mu.
Okay, yeah, mu. All right, if you look up argon on the periodic table, you will see 39.948. But that's in grams per mole. So I am going to tack on 10 to the negative third to convert it from grams to kilograms. And I start crunching my numbers here. This is going to give me all of these multiplied across the top there are going to give me 7682.6. And in the bottom, I'm going to move my decimal place and get 0.039942. All of this is still under my square root symbol. At this point, it would give me 192,315, and it's the square root of that. And so once I finally get all the crunching and I've done the square root, I should get 438 and a half. And this is in meters per second. Now, one of the things, this goes back to reality check things. One of the things that is true about root mean square velocity is that you will very seldom see it in less than 2 digits. So you are unlikely to see it at less than 10 meters per second. That's like really, really rare. You have to have a super, super cold temperature. The other end of this is you're probably also really unlikely to see this at more than about 1,000 meters per second. So there's kind of a benchmark on either end there. This is a way to kind of judge whether or not you've done your math correctly or not. So if you get a number bigger than 1,000, be suspicious. If you have a number less than 10, be suspicious. Okay, not that you can't get numbers like that, but it's really rare. If you look at the textbook examples, you will see that they also fall typically in the hundreds. That's kind of like the usual way that it works. All right, one more equation for this particular chapter that also involves square roots. All right, but first, 2 words. All right, we've got diffusion. Okay, and diffusion is mixing of gases. So if you had a slow leak in your tire, as the air is leaking out to join the exterior air outside your car, it would be happening at a slow speed as the molecules begin to mix together. I had the great joy of having 3 nails in my tire on Sunday. I drove to one of the local supermarkets that's referred to as E-Mart, and got there, and you know the idiot light on your dashboard that says you have a low tire. And at first I thought it was because the temperature had changed, because sometimes it does that. But then I walked around the car and I had to look twice, and there's like 3 nails jammed in one of my tires. It's like, yeah, that was not good. But mixing of gases. All right. Effusion. Effusion means something different, and it sounds like a middle school bad joke because it is the passage of gas through a tiny hole into an empty space. Like I said, kind of sounds like a really bad middle school level joke. Think of it more along the ideas of if you have gas molecules escaping from a container, the size of the gas molecules makes a difference. And Graham's law, more famous dead guys, of effusion is the equation for this. This is another one that has a couple, or has two square root signs in it. So we've got rate of 1 over rate of 2. Okay, that's the left-hand side of your equation. On the other side, it's square root of the molar mass of number 2 over square root of the molar mass of number 1. And yes, I know that was backwards. Because on this side, it's 1 over 2, and on that side, it's 2 over 1, but yeah, that's the way it's designed. All right, let me give you a comparative idea here about how this works. Okay, and since I can't really draw, this is a piggy bank. I know, I have no art skills whatsoever. Okay. If you have a piggy bank full of coins, okay, in the US, the coins that we have options for are, we have pennies, we have nickels, we have dimes, we have quarters, and there's not really a whole lot of $50 in circulation anymore. So we're going to kind of ignore the $50 idea. If you turn your piggy bank upside down and you try to shake the money out of it, because you don't want to break your piggy bank, size of the coin to some degree determines what comes out first. Not monetary amount, size of the coin. Okay, so US money, dimes are basically the smallest coin. For an average diameter, they have the thinnest thickness in comparison to the other 3 coins that we're talking about here. So if you start shaking the piggy bank upside down, you're probably going to get more dimes coming out first, not exclusively, just predominantly. Then probably some of the pennies are going to come out with the dimes because they're only slightly thicker than a dime, and they're really similar in size as far as the diameter goes. Nickels are thicker, okay? So nickels and quarters are probably going to come out a little bit slower, statistically speaking, because they are either thicker or because they have a larger diameter, okay? Why is this all relevant? All right, this is a comparison here. And the idea is if you have 2 types of gases, their molar masses, because diameter is sort of basically tied into the idea of their molar mass, that's going to give you a way to compare how likely these things are to actually come out through the opening where they're leaking out. Weirdly, you actually don't do anything with the left-hand side of the equation. I don't know why it's designed that way, it just is. So if I wanted to compare the effusion rates of neon and argon. Now, it is in the nature of the way these problems are done that textbooks tell you whichever gas is listed first. So we're going to call neon number 1, and we're going to call argon number 2, only because that's the way the problem's worded. If I then put it in my equation, rate of neon over rate of argon is going to give me then square root, only I'm going to put argon on the top. And argon is my 39.951, square root of 39.95. I'm going to put my neon's mass on the bottom. Neon has a mass of 20.18. Crunch all my numbers, do my division. Eventually, I'm going to get the number 1.4. Now, if you start looking in the back of the book about where some of these answers are like reported, if you're looking at examples, they will often give you a phrase. So the phrase would be that neon effuses 1.4 times faster than my argon. So it's kind of like a little phrase slash sentence. Little things travel faster than big things given the same temperature. This is another one of these equations where we are making assumptions. We're assuming that we are not changing temperatures while this is an in-progress event. Because if you change the temperature, then that's going to change how fast things are flying through the emptiness. So in this case, little one travels faster than big one because neon is a smaller atom than my argon is. And that actually gets us all the way to the end of the chapter. So let me gather up my webcam and see if I can go back in the other direction.
I pushed the little glimmy thing.
Okay.
There.
Oh, yeah, okay. Just gonna start my camera. Yeah, yeah. Some strategic rearranging of my webcam here.
Bring it down. We see your chin.
Yeah, I just realized it's hanging. Like I said, my art skills are awful.
Like it's the witch of Annecy graph.
All right, that's probably not too bad. All right, so that's the end of the chapter. Let me talk about the homework set for a moment. Let me twist around and grab up my physical page for the homework set. All right, so chapter 9 homework has 3. Do I actually have audio?
Yes,
Okay,
ma'am.
it's like doing this, it's like giving me this weird message again of your speaker is not working. That's very weird. I have not had this problem before. I don't know if it's because I have my webcam plugged into a different USB over than I normally do. Irrelevant trivia. I had a birthday. I got wireless headphones, but my computer is not Bluetooth enabled. So I had to buy a widget to like stick in the USB to make it work. Why are you back there with the cat?
She blends into the shadows. You can't even see her.
Yeah, my black cat. So 3 conversion factors are the first set there. We've got from millimeters of mercury to atmospheres, atmospheres to torr, and pascals to atmospheres. Then we start sort of progressing through the laws that we've been doing: Boyle's law, Charles' law, Gay-Lussac's law, ideal gas law, PV equals nRT. And then combined gas law, the one that has P's and V's and T's all in the same one. And a tip when you get to number 9, make sure you are doing this like a traditional stoichiometry problem. It's got to have 3 steps to it. And the variant on the ideal gas law, the one that involves density, there is a Dalton's law problem, root mean square velocities, and Graham's law of effusions. So all of those things are covered then as part of the homework set. Questions?
The definition of effusion, you say that's passage of gas through a tiny hole into empty chamber.
Mm-hmm.
Empty mean vacuum, right?
Yes, into a place that does not have another gas. That's
so
true.
Basically, it's all just for some laboratory, right?
Yeah, I mean, it's a calculation that doesn't have, I don't know, truthfully, I don't know what the application would be for effusion, although thinking back though, maybe it doesn't have to be a vacuum. Maybe it just has to be some place that has lower pressure. Otherwise, the gas would not pass into a space that had higher pressure because there'd be a backflow. So, yeah, I'm not sure. I'm not sure if it has to be a vacuum, but it would definitely have to be lower pressure than where the gas is escaping from.
Okay.
Other questions? All right, let me switch this. Okay, this makes homework then due Tuesday. So that gives you the whole weekend to finish up your homework set. Let me switch to a different notes page here, which is thermochem. Talk a little bit about thermochem today. Pretty much everything that we've been doing all the way from the beginning of the semester to we're at about halfway, keeping in mind if it is relevant to you that the W date is approaching. Everything we've been doing has been matter. Well, now we need to talk about energy a little bit. We've been kind of hinting around. We mentioned joules a little bit in the first chapter. We mentioned joules here as part of one of the R values for the gas laws. Now we have to kind of talk about it in more depth. If you think about this on a more sort of universal scale, energy is the flip side for matter. I have a really appalling t-shirt that says "You matter" on the top line, and then under that it says, after it says "You matter," it says, "Unless you multiplied by speed of light squared, then you energy." Bad science jokes. But the two are interchangeable. We have mastered one direction. We have mastered the take the matter and turn it into the energy. Nuclear reactions are a prime example of this. But it also happens in our sun. The sun is made mostly of hydrogen. And as it is slowly over the lifespan of our little galaxy here, being converted from hydrogen into helium and eventually into some other elements, we are doing from matter to energy, which is a vast, vast release of energy. Back to the nuclear reactor idea. It's like the amount of uranium that goes to fuel an aircraft carrier is less than a couple 100 kilograms, and you can fuel something the size of an aircraft carrier with it. So you have this huge, vast, like, conversion rate thing going. If you go onward to take the second half of this, we will talk more about some of the basics that go into the conversions, and also the things you get in terms of other elements when this happens. This whole chapter is a little bit of an overlap between chemistry and physics. So some physics ideas get thrown in here. Energy can be defined a couple of different ways. One way is to call it the capacity to do work. But you can also say that energy is the ability to produce heat. Both of them fall in the category of an energy. Well, then if we divide the big overarching category of energy into a couple of broad categories. There's kinetic. Kinetic is energy due to motion. So if you are an electron moving, or if you are an elephant moving, you have kinetic energy. Obviously, there's a mass difference. There's also probably a velocity difference too. When you do physics, one of the things that a lot of the initial phases of physics harp upon is the fact that velocity and speed are not actually the same thing. Velocities involve a direction, which then ties into the little equation there that's shown of KE, kinetic energy, is 1/2 mv squared. So if you're an electron, your mass is really low, 10 to the negative 28th grams, more or less. But you're probably traveling pretty close to light speed. Not exactly, but close. So massive velocity, really light mass, but you still get kinetic energy out of it. Charging elephant involves much greater mass, but you're not traveling at light speed unless, if you're an elephant, you're not traveling at light speed. So your velocity is a lot lower. But your kinetic energy is pretty massive because there's such a big mass difference. So the two of them are, the two ends of the idea are kind of bothly relevant there. Both of them change how much kinetic energy you have got going. I have a writer friend of mine who he quoted a book to me that I am actually not familiar with, in which a hard-boiled detective takes a bullet out of his gun and holds it in his hand and throws it, literally with his fingers, throws the bullet at the guy he is threatening and says to the guy, "The next one will be faster." Same massive bullet, firing it from a gun versus throwing it with your hand, there's a pretty big velocity difference there. Thermal energy, like we said, energy is the ability to produce heat. So thermal energy actually gets lumped into kinetic energy. And I have a little embedded video here, which probably won't open up, but you can go back later and click it. Let's see if this actually opens. This is my favorite kinetic and potential energy video. So that way you get, oh, and now it's actually trying to load something else. Oh, phooey. Yeah, more Wile E. Coyote videos. Anyway, back to kinetic and potential here for a moment. But anyway, you go back and watch the video. When he pushes the rock off the edge of the cliff, up until it actually falls off the cliff, it's potential. It has the ability, due to position, to exert force. But until it actually falls off the edge of the cliff, it's just moving in a horizontal direction. Well, then, of course, it rolls down the curve and doesn't hit the Roadrunner, and rolls back up the other direction. And as it's beginning to curl back up around before it squishes him, it's then changing from kinetic back into potential. Now, granted, this is why we are talking Wile E. Coyote and the Roadrunner here. So we're violating a number of laws of physics, including the fact that chances are the boulder would not return to the exact same position, because conservation of energy is a thing, as well as friction. But all of these pieces kind of give you some nice visuals to go with it. So potential can be due to position, but potential can also be due to composition. If you put gas in your tank of your car, up until the point where you turn the ignition and now it's running the car, it only has the possibility to do work. All of those little carbon to carbon and carbon to hydrogen bonds are storage of energy, because gasoline is mostly octane. I mean, these days it's got some ethanol in it too, but it's got carbons and hydrogens all bonded together. Up until you burn it, up until internal combustion happens, it's just potential. So all of these things are going to play a part into all of the rest of the thermochem that kind of comes in the upcoming chapter there. And we're going to talk more eventually about law of conservation of energy and some other things that we will eventually be doing in lab. We are toward the end of the semester. I think it might be the last lab before Thanksgiving. It might actually be the last physical lab, possibly. We will be doing some thermochem based stuff for lab itself. And since I have a batch of you for lab, remember, okay, Monday is lab again. And as I squirm around here and look at my schedule, so everybody should have done the hydrate lab at this point. The next pairing of labs is limiting reactant and chemistry of copper. So my A group people, I will see on Monday to do the limiting reactant lab. I have loaded all the videos for the copper cycle lab onto the lab section of Canvas. There's 8 pictures. Actually, no, wrong lab. There's 6 videos. Actually, it's 5 videos and 1 picture, because I goofed up and I was doing things while people were in lab, and one of the things that I intended to do a video a 2-minute video of didn't actually, it happened by itself because I left it alone for too long. But there should be a little video for each of these steps A through F, I think it is, for that lab. So that's something that if you are the B group, you should look into watching for next week. Questions about homework, which is due next Tuesday, or lab stuff?
I just want to let you know that McHugh's class still hasn't done the metathesis or metathesis lab yet.
He didn't load a set of photos for that?
He has not yet. He's emailed back saying he will, but
Okay.
we still haven't done it.
Okay.
Just in case you're gonna put questions about that anywhere.
It's stuff that was actually on the last test, because precipitation reactions, gas generating reactions, that was actually stuff that was from chapter 4.
Oh, okay.
So
Well, then I guess
from a
we're through it.
lecture point of view, we've already covered that.
Sounds good.
Okay, and so some of you I will see on Monday, and everybody else I will see on Tuesday. And I'm going to change I'm going to insert a due date then for the Chapter 9 homework so that it shows up on your Canvas shell. And I will see you next week.
All right. Thank you.